So in this topic, we are learning how to build a third-person 3D game with a focus on character movement and animation. So a third-person game means that the camera is outside of the player character, looking at them from behind or above. So unlike a first-person game where a view is the from the character's eyes, this view is common in adventure games. So let's break this down into uh, multiple steps. So first step would be setting up the scene. So you'll start by creating a game environment. This will be a room with walls, floor, lights, similar to what we did in other topics when we built a first person game. So in a third person game, the camera isn't attached to the player's perspective. So the environment is viewed uh, from outside the character. You'll uh, you'll reuse the basic room from other topics uh, and just remove the first person player and scripts. This will give us a blank room to work with. Uh, Next step would be import character model. So for the player character, we'll use a 3D model uh, of a 3D model of a humanoid, which means a model that looks like a person with the head, arms, legs, etc. So in a third person game, the player can see their character, so it's important to have a detailed model instead of a simple capsule we use for the first person game. So this model is made up of vertices, polygons that define its shape. And the next step would be position the camera. So the difference between a first person and a third person game is the camera placement. In the third person view, the camera is positioned outside and behind the character, so the player can see their character moving around in the game scene. So you'll set up the camera to follow the player as they move, but instead of being inside the player's head like the first person. So it will orbit around the character. The camera will stay focused on the player, allowing them to move while the camera tracks them from a distance. And next up would be writing movement scripts. So next you'll write the code that makes the character move. That this includes running, jumping, and turning smoothly. So instead of just sliding the character across the floor, we want to make sure that the movements are realistic. For this, you'll use something called lerp, lerp, which stands for linear interpolation, to make sure the characters rotation and movement are smooth instead of a instead of sudden movements. So the movement script will listen for the player's input, which is the keyboard or the gamepad, and move the character accordingly, whether they are walking, running, jumping. So the jump will be controlled by detecting when the character is grounded, so they can't jump endlessly while in the air. And the next step would be real-time shadows. So because the camera is outside the character, shadows will make the game more visually realistic. So you'll set up a real-time shadows so that the character moves and the shadows move and change shape, adding depth to the game scene. So the lights you place in the scene will cast shadows from the character and the objects. And the last step would be playing animations based on movement. So finally, you'll add animations to the character. So animations make the character move realistically when they walk, run, jump. So instead of the model just sliding across the floor, it will animate the legs moving like moving when walking or running, the player's input will trigger different animations. For example, when the player presses the run button, the character will switch to running animation. So animations are applied to the character model based on the player's actions. So this way, when the player presses a key to move forward, the character's walking animation will play, and if the player jumps, the jumping animation will be triggered. So basically, you'll import a humanoid character model. This will be the player's visible character. And next we set the camera to orbit around the character. So the camera will follow the player from the outside of the character, and will write movement scripts. They'll control walking, running, jumping, and will add shadows for visual realism. Shadows will move with the character, adding depth to the scene. And last step would be playing animations for realistic movement. So the character will animate according to the player's actions. So that's the overview of this topic. So next, to understand how to set up uh, a third person view in Unity, we'll walk through importing a character model and positioning the camera in a way that allows us to see the character from the external perspective, just like a popular third person game such as Legend of Zelda or Uncharted. So let's go step by step. First step would be importing the character model. So first you need to import the character model into your Unity project. You'll be using two files, FBX and TGA. So FBX is which contains the 3D model, and TGA file which contains the texture that defines the look of the model surface. To do this, you basically simply drag the FBX file from your computer directly into your Unity's project view, or you can use import new asset option in the project view. And next step would be setting up the model's import settings. So after the model is imported, it appears in your project view. So when you click on it, you'll see its settings in the inspector. So there are two key settings we need to adjust here: the scale factor and the normal settings. So scale factor is the model may appear too small or too big because of different unit settings in various 3D modeling softwares. So to fix this, change the scale factor to something like 10 to make the model the right size for the Unity scene. And we have few normal settings, which are normals are invisible lines that point outward from the model's surface, helping Unity determine how light should bounce off the model. So if the normals from the 3D model are not correct, the model will react oddly to the lighting. So change normals from import to calculate to let Unity fix this automatically. So after these changes, simply click apply to make sure the settings take effect. And the next step would be applying the texture to the model. So next, import the TGA file, which is your texture file, which is the texture of the model. So this texture gives the character its color and details. So when you go to the materials tab, you'll find this in the inspector tab, for the character model. You'll see extract materials to generate a material for the model. So now find the material that appears in the project view and basically drag the texture, which is your TJA file, onto the albedo texture slot of the material in the inspector. So after applying the texture, the character may not look significantly different depending on the texture, but the details like painted shadows and highlights will improve the model's visual quality. And next step would be placing the character in the scene. So now that the model is set up and textured, you need to place it in the 3D world. So you basically drag the character model from the project view into the scene view and position the model, which puts the character, uh, make sure the character is in the center of the room, and lifts it slightly above the floor so it's standing properly. So now your character will be ready in the scene, although it won't move and or animate yet. So after placing the model, you'll notice that the character's arms are stretched straight out to the sides. Uh, is what's called a T pose. This is completely normal. The T pose is the default stance used by 3D models before animations are applied. So next we'll add animations to make the character move naturally. So by following these steps, we can successfully import a third person character into Unity, placed placed in it in the scene, uh, which uh, which will be prepared for further development. So the next step will include positioning the camera properly and writing scripts to control the character's movement. So this step is important in creating the third person game, as it allows the player to see and control the characters from a view outside of their body, which is defining the feature of the third person games. So next would be adding shadows to the scene. So to add shadows to a scene in Unity, it's important to understand how shadows work in the virtual world and how they are managed by Unity. So in real life, shadows happen naturally, but in the game, we have to control them through settings and code. So so shadows in Unity are created by lights in your scene. So one common type of shadow is called real-time shadows. These are the shadows that change and move as objects and lights in the game move, making the scene more dynamic and realistic. So by default, Unity adds a directional light to every new scene. So this is like the sun shining from one direction. So for shadows to be visible, you need to make sure that this light has shadows turned on. So to check or enable shadows, you basically select the direction light in the hierarchy and go to the inspector panel, and you'll see shadow type setting, and set it to soft shadows for smooth shadows, or hard shadows for sharper edges. So there's also an option for no shadows if you want to disable them. So real-time shadows are important for moving objects like characters, because they need to update continuously as those objects move in the game. And light maps. So light maps are a different way to create shadows, especially for objects that do not move. Instead of calculating shadows in real time, light maps are shadows that are baked or pre-calculated or and drawn onto the textures of objects like walls or floors. So these shadows don't move because they are static. However, they look very realistic because the computer can take its time to calculate how light and shadow interact with the scene when you build the game. So instead of doing it while the game is running, so light maps are very effective for static objects like buildings or terrain. So because they save the computer from having to calculate shadows during gameplay. And we can combine real-time shadows and light maps So you can use both real-time shadows and the light maps in your scene for better performance and visual quality. For example, characters and other moving objects can use real-time shadows, while static objects like walls can use light maps. So you can control which objects use real-time shadows by using a culling mask setting on the lights. So this lets you choose specific objects that should cast real-time shadows while leaving others to use light maps. So this balance helps keep the game running smoothly, because real-time shadows can be demanding for the computer, while light maps are pre-calculated and easier to handle. And object shadow settings. So every object in your scene can either cast shadows, which or receive shadows. What I mean by cast shadows is basically create shadows, and receive shadows is basically gets darkened by shadows from other objects. So you can control this using a mesh renderer or skin mesh renderer components in the inspector for each object. For example, you might want your character to cast shadows onto the ground but not receive shadows from the environment. So depending on how you want the scene to look, and then choosing the right shadows for your scene. So if your scene has lot of movements, you'll rely more on real-time shadows for characters and objects that move. For stationary parts of your scene like buildings or terrain, light maps are a great choice because they look realistic and don't require extra processing while the game runs. So adding shadows to your scene in Unity involves turning on real-time shadows for moving objects and using light maps for static ones. So this helps balance the look of the game and its performance. So real-time shadows are great for dynamic scenes, while light maps give you pre-baked realistic shadows for non-moving objects. So that's about shadows. Um Next topic is orbiting the camera around the player character. So when developing a third person game, one key feature is to have the camera follow the player from behind or above, so allowing the player to see the character and its surroundings. So unlike in the first person games, the camera here must move independently of the character's rotation. So let's go step by step on how to set this up in Unity using a custom camera orbit script. So first thing is the camera position. So we first place the camera above and behind the character at a fixed distance, so that the player is always visible in the scene. Like for example, you might set the camera's initial position like something like to 0, 3.5, minus 3.75, which places the camera slightly above and behind the player model. And next step would be creating orbit camera script. So to enable the camera to move independently but stay focused on the player, we create a C# script called, you can call it orbit camera. This script will control the camera's movement around the character and ensure that the camera always looks at the player even while rotating. So let's go to the script. So in this script, we have a serialized field transform target. This variable is where we store the reference to the player character, which is the target. By using the serialize field, we can assign the player model directly from the Unity's inspector, and we have a public float uh, rotation speed. So this controls the speed of the camera position. You can adjust this to make the camera rotate faster or slower. And we have a float, private float rotation y. This variable keeps track of the camera's current y-axis rotation, which is the rotation around the player. And we have private vector 3 offset. So this stores the initial distance between the camera and the player, allowing the camera to maintain the fixed distance while orbiting. And in the start method, we have a rotation y. So this line of code, we initialize rotation y to the camera's current y-axis rotation, which is with this makes sure this makes sure that the camera rotation starts based on its initial position of the scene in the scene. And we have a offset target dot position, so minus transform dot position. This line calculates the initial distance, which is the offset between the camera and the player. By storing this value, the camera will always maintain the same relative distance from the player as it moves around. And we have a late update method. So in the late update method, this method is called after update, uh, and ensures that the camera moves after all player movements and updates have occurred. So we have a float horizontal input. So this reads the horizontal input, which is arrow keys A and D. If the player presses these keys, the camera will rotate around the player. And we have a if statement. So we check if there's horizontal input, which is the arrow keys. If there is, the camera rotates using the input. If not, it checks if the it checks for mouse movements to control the camera rotation instead. And else we have else. So this if the player is this line of code, if the player is pressing arrow keys, the camera's y-axis rotation changes based on how much the player is pressing, scaled by rotation speed value. And sorry, this one. So yeah, this one is used for how much the player is pressing, scaled by the rotation speed value. So the else, if there's no arrow key input, this line rotates the camera based on the horizontal mouse movement, but at a faster rate, since mouse movement is usually more subtle. Um, and next, so a quaternion is a data type used for handling rotations in Unity. So this line converts the y-axis rotation value, which is the rotation y, into a rotation. And transform dot position. Uh, this line is crucial for moving the camera around the player. So by rotating the initial offset, the position of the camera relative to the player, using the quaternion, we calculate the new position of the camera, and the camera stays at the distance at the same distance from the input by but moves around them. uh, and we also have look at transform dot look at. This is a method. Look at is a method. This ensures that the camera always faces the player character regardless of the camera's position. Without this, the camera could orbit the player but end up looking in the wrong direction. So what does this script achieve? It's basically achieves smooth camera orbiting. So the camera rotates around the player character based on arrow key or mouse movement, and it maintains distance. The camera keeps a constant distance from the player, which is set by the initial offset. And it also the script follows the player, so the camera always looks at the player character, ensuring that the player is always visible in the center of the screen. So so to the to see this act in action, you attach the script to the camera in Unity and drag the orbit camera script to the camera, and assign the player character in the inspector of the camera, assign the player character as the target, and when you play the you'll be able to control the camera around the player either using the arrow keys or the mouse. So that's about camera. Next topic is camera relative movement controls. So the goal here is to program movement controls for third person character where the character's movement distance is based on the camera's position or orientation. This type of control is known as camera relative movement. So first, so in a third person game, the character should rotate to face the direction in which the player wants to move. So based on input like arrow keys WASD, the direction of the character faces is relative to the camera's position. So if the camera is facing north, the player presses left, the character will move west. So to accomplish this, we need to detect the player's input with using the arrow keys or WASD, and we calculate the direction the character should face based on the camera's position orientation. So and then you rotate the character to face that direction. So we for that we create a relative movement script. So in that script, let's go to the script relative movement. So in this uh, script we have a horizontal input. This detects the left or right arrow keys, which is A or AD keys, and we have vertical input. So vertical input detects the up and down arrow keys or W and S keys. So these values range from -1 to 1 depending on which key are pressed. So the script calculates two important directions. Right is the direction to the right of the camera, determined by target dot right. This gives the camera's uh, local local right, and we have a forward. Forward is uh, calculated using a cross product between the camera's right and the world's upward direction, which is vector 3 dot up. This gives us a direction that's perpendicular to the ground. So the character moves uh, along the ground, not up or down. And next, the final movement vector is calculated by multiplying the horizontal input with the right direction and the vertical input with the forward direction. This ensures that the character moves relative to the camera's perspective rather than its own. And we also have a quaternion, which is this this function creates a rotation that faces the direction of the movement vector. So this is applied to the character rotation, which is transform dot rotation is equal to this line of code. So when the player presses the keys, the character rotates to face the correct direction. So right now the character snaps instantly to a new direction. So, but it would look much better if the character rotated smoothly. So for that we use lerp, lerp, which is short for linear interpolation. So to achieve this, yeah, I think it was not added in this code, but we use linear interpolation, which is quaternion dot lerp. So this function gradually rotates the character from its current position, which is transform dot rotation, towards the target rotation, which is the direction. And we also have a third parameter, which is yeah, the third parameter is basically rotation speed multiplied by time dot delta time, which controls the speed of the rotation. So the time dot delta time ensures that the rotation speed is consistent regardless of the frame rate. So with this adjustment, the character smoothly turns towards the direction of the movement instead of snapping to a new direction instantly. So uh, so what does camera relative mean? So camera relative movement means that the character moves in relation to the camera's perspective, so not on its own. For example, if the camera is behind the character and the player presses the right key, the character will move to the right of the screen regardless of the character's current facing direction. So if the camera is in the front of the character and the player presses right, the character will still move to the right of the screen, which is the character's left in this case. So this system makes the control more intuitive for the player because left and right always corresponds to the screen rather than the character's personal orientation. So this script, relative movement script, enables smooth camera relative movement by calculating movement based on the camera's position and rotation, and using the lerp to ensure that the rotations are smooth. And this is a common and intuitive control system used in many third person games. And the last topic for today is so we'll go through how to make a player character move in the third person 3D game using Unity's character controller. So how to handle movement input from the user. So we'll walk through the code and the concepts step by step. So first, to control the character movement, Unity provides a built-in system component called character controller. So the character controller helps manage movement without using the Unity's physics engine, which is directly making it perfect for player movement in most games. So to add a you select the player object in the Unity editor and go to components, physics. You'll find character controller and adjust the radius to fit the the character model better, and then you write a movement script. So relative movement, yeah. So relative movement script, again we go back to the relative movement script. So here we have a require this line of code. This line ensures that the game object uh, the script is attached to will always have character controller component. It's a safeguard to make sure you don't forget to attach this important component, preventing errors. And we have public and private variables. We have a public move speed uh, move speed. This is a public variable that controls how fast the player moves. It's public so that you can easily tweak the speed from the unity's inspector. And we have a character char controller. This is a reference to the character controller component attached to the player, which we'll use to apply the movement later. And then initializing the character controller, start method. So get component character controller. So this is used to get the character controller attached to the player game object. We store this to so that we can use it in the update function for moving the player. And handling input. So float, yeah, float horizontal input. I think we discussed this. So in this we have input dot get access horizontal, input dot get access vertical are the Unity's built-in methods to detect player input from the arrow keys or WASD keys. Horizontal is left-right movement, vertical is forward and backward movement, and then we calculate the movement direction. So here vector 3 movement. So this we check if any input is detected, which can be horizontal or vertical. If there is no input, the player will remain stationary. Right is equal to target dot right. This gets the right direction relative to the camera, and we have forward is equal to vector 3 dot cross right, vector 3 dot up. This calculates the forward direction relative to the ground. We use a cross product here to ensure that the player moves along the ground plane even if the camera is angled. And the final movement vector is the combination of horizontal and vertical input scaled by right and forward directions. So that's about calculating movement direction. Next, we apply the movement speed. Uh, movement speed, movement speed. Okay. So movement, we multiply the movement vector by movement speed to determine how fast the player will move. And we have vector 3 dot clamp magnitude, which ensures the diagonal movement when both horizontal and vertical keys are pressed doesn't make the player move faster than intended. And we apply the rotation to the player, which is the transform dot rotation dot is equal to quaternion. So this smoothly rotates the player to face the direction of the movement. If the player presses a key to move left, for example, the character will rotate to face left. And the last step would be applying movement to the character controller. Where is that? Yeah, it's here. So time dot delta time ensures the movement is frame rate independent, meaning the character moves at a consistent speed regardless of how fast the game is running. And finally, we have a char controller dot move, which applies the calculated movement to the player. This makes the character move in the direction we calculated. So we'll discuss the other code later. So here we discussed about character controller, which is a component that allows you to move the character without needing to handle complex physics. And we discussed about input dot get access, which is a method used to detect player input for horizontal and vertical movement. We also discussed about clamp vector 3 dot clamp magnitude, which is used to limit movement speed when moving diagonally, and quaternion dot look rotation, which smoothly rotates the player to face the direction of the movement. Time dot delta time ensures that the movement is smooth and frame rate independent. So by understanding each part of this code, you can modify or extend the functionality as needed, such as adding jump or. So the next step would be handling vertical movement like jumping. We'll do that in the next session. That's all for today.